Forward time travel is a concrete physical mechanism baked into the very laws of the universe. For centuries, Isaac Newton's physics dominated our worldview. It taught us that a single, invisible, universal clock ticked at the exact same rate for everyone, everywhere in the cosmos. That changed in 1905. Albert Einstein realized the speed of light is the only true constant. For this to be true, time itself must stretch and compress to accommodate an observer's motion. Einstein's theory implies that time is no longer a fixed boundary, but a dimension we can navigate using speed and gravity. In 1971, Joseph Haffel and Richard Keating put this to the test. They loaded 4 high-precision atomic clocks onto commercial airlines and flew them around the world to see if ordinary motion could alter time. When the flights returned, they compared the airborne units with the stationary reference clocks at the U.S. Naval Observatory. The two sets no longer matched. These results were measured in nanoseconds. The eastbound clocks lost time, while the westbound clocks, traveling against the Earth's rotation, gained time relative to the ground. We rely on this physics every time we use a phone. GPS satellites orbit at high speeds, making their onboard clocks tick slightly slower. However, being further from Earth's mass, the weaker gravity speeds them back up. Engineers must account for a net gain of 38 microseconds daily to maintain accuracy. Without these exact relativistic corrections, your GPS position would drift by about 10 kilometers every single day. When these micro-adjustments are scaled up to extreme velocities, the result is the twin paradox, a scenario where a traveler's biological age diverges completely from those they left behind. We see the beginnings of this with astronaut Scott Kelly. After spending a year on the International Space Station, he returned to Earth slightly younger than his twin brother, Mark, who remained on the ground. The traveling twin undergoes acceleration to return home, breaking the symmetry and shifting them into a different reference frame. As this space-time diagram shows, the traveler accumulates less proper time, experiencing 5 years on their journey, while 6 years elapse for the stationary twin. Under continuous acceleration near the speed of light, this gap widens until decades of space travel begin to outpace centuries of Earth history. Special relativity proves that high velocity untethers a traveler's lifespan from the rest of humanity, acting as a direct path into the future. Beyond speed, general relativity provides a second mechanism for time travel. It describes gravity not as a simple pull, but as a physical warping of space-time itself. The closer an observer is to a massive object, the slower time passes for them relative to someone in deep space. This effect is most extreme near a stellar mass black hole, where the gravitational gradient is overwhelmingly steep and dense. Supermassive black holes create the most significant gravitational time dilation in the known universe. At these extreme scales, spending just 5 minutes near an event horizon could mean returning to an Earth where months or even years have already passed. Extreme gravity allows a traveler to effortlessly outlast entire generations of human history, using the natural geometry of the cosmos to leap forward. Current engineering limits mean we cannot yet generate the continuous kinetic energy required to achieve these relativistic speeds. Bridging this energy gap is the focus of theoretical work on traversable wormholes and systems for long-term biological stasis. If we can't move fast enough, we must rely on cryogenic pods, preserving human life for the centuries it takes to reach a destination. We are all time travelers moving forward at a fixed rate, but the equations of physics provide the map to fast forward. But reaching an unrecognizable, highly distant future version of Earth highlights the extreme isolation of this long journey. The physical laws of the future are real, but they come with a permanent cost. You can never return to the present.